Hello students, how are you? Hope you are doing well. Now the question is, derive an expression for potential energy of an electric dipole P in an external uniform electric field E. When is the potential energy of the dipole part 1 maximum and part 2 minimum? So the problem is based on the topic the electric dipole and the derivation of its potential energy. Now the situation is like this. There is a uniform electric field. Suppose these are the electric field lines. And in this particular electric field, a dipole is placed. So this is the dipole. This is the negative Q charge and this is the positive Q charge. This is the angle which the dipole is making with the direction of the electric field. And suppose the length of the dipole is 2a. So this is the length of the electric dipole. Now we have to calculate the potential energy, and potential energy is a kind of a stored energy, and the energy is stored in this particular dipole when a certain work is done on it. So suppose a work is done on it to rotate this dipole. Suppose work is done to rotate this dipole, electric dipole from an angle of theta naught to an angle of theta. Suppose we rotate this particular dipole from theta naught angle to theta, and in this particular process some work is done, and this work is basically used to store the energy in the dipole. So this particular work can be calculated by this formula. W equals to integral tau d theta, where the limits are from theta naught to theta. Suppose the dipole is moved from angle theta naught to theta, and this is the torque and d theta. Now torque, we know that it is equal to P cross E. The torque for an electric dipole is given by this formula, P cross E, which is equal to PE sine theta n cap. So we put this expression here, PE sine theta d theta, and the limits are from theta naught to theta. Now P and E are uniform, it means they are constants, so we can pull them out of the integration. So we get this expression as PE integral sine theta d theta, and the limits are from theta naught to theta. These are the limits. After solving is, we get this value as, final value as minus PE cos theta with limits from theta naught to theta. After putting the respective values, we get this expression as PE cos theta naught minus cos theta. Now let us take theta naught equals to pi by 2. The particular dipole is at the initial position at theta equals to 90 degrees, and it is moved from a position of 90 degree to a certain angle. So we put this value as theta naught equals to pi by 2. So we can say that W equals to PE cos pi by 2 minus cos theta. And we know that cos pi by 2, which is cos 90 degree, is equal to 0. So this value becomes PE cos theta. This is the work done, and the work done is equal to the potential energy stored. So the potential energy stored in the particular electric dipole is minus PE cos theta. We can write it down in the vector form also. It is equal to minus P dot E. So this is the expression of the potential energy of an electric dipole placed in an uniform electric field. Now the first part is when it is maximum. So to maximize this expression, we have to make this particular value P dot E largest, and this is a negative sign here. So if this particular expression is also negative, then negative into negative becomes positive. So we can see that if theta is equal to 180 degrees, then we know that cos 180, cos theta means cos 180 is equal to -1. So at theta equals to 180, the value of u theta, which is equal to u of 180 degrees, is equal to P dot E, because, or we can say that P into E into cos 180, and cos 180 is -1, -1 into -1 is +1. So we get the maximum value as P dot, P into E. This is the value of u at the theta equals to 180 degree angle. Now when we have to minimize it, we have to make this particular expression as +1, because the minus sign is in front of it. So when theta is equal to 0 degrees, u of theta becomes minus PE. So this is the minimum value of the potential energy stored. So the maximum value of the potential energy stored is PE when the angle theta is 180 degrees, and the minimum value of the potential energy is minus PE when theta equals to 0 degrees. So this is the particular solution of this particular problem. So hope you understand the solution. Thank you.